The big factory breakthrough is not a new robot arm. It is making changeover feel like a software release, not a construction project. In the best version of the autonomous factory, you do not rebuild the line. You update validated motion plans, tool settings, vision models, schedules, and safety limits. You might swap a fixture or an end effector. Then you prove with evidence that the new behavior is still safe and still in spec. That framing matters because industrial robots are already mature at many tasks: welding, painting, pick-and-place, palletizing, machine tending, inspection, and semiconductor handling. These are well established. The frontier is flexibility. It is the ability to reprogram across variable products, shifting suppliers, and messy production conditions without weeks of integration work. So what actually makes a factory programmable in 2026? It is a stack, not a single product. You have robot arms and mobile platforms. You have programmable logic controllers and safety-rated controls. You have machine vision, industrial networks, manufacturing execution systems, and digital twins. You have optimization software, and you have human approval workflows that decide what is allowed to change. One uncomfortable detail is that these layers are rarely interchangeable across vendors. Even when two components are both standard, they often do not plug together without custom glue. Integration labor becomes the hidden tax, and vendor lock-in becomes the silent ceiling on what the factory can become. That leads to the first high-impact finding for strategy leaders. Stop buying robot count, start buying changeover capacity. Installed robots do not equal reprogrammable production. Value shows up when motion, tooling, sensing, quality, and scheduling can all be reconfigured together. If you want a board-level metric, it is not how many robots are on the floor. It is time to new product. It is time to recover from a fault. It is exception rate, validation effort, and how often an operator must intervene to save the run. Those are the numbers that tell you whether the factory is becoming software-defined or just more automated. Now, where does machine learning fit in? Learning systems already help in several roles. They can improve perception and classification. They can support scheduling decisions. They can detect anomalies and help learn policies for sequential decisions. But robust deployment in contact-rich physical settings still depends on constraints and coverage. You need bounded models, test suites, fallback logic, and engineered safety cases. A factory is not a web service. A small error can become a crash, a quality escape, or a safety incident. This is why hybrid control is a practical North Star. Combine learned perception with formally bounded motion, force, collision, and process constraints. Use models that can be inspected. Wrap autonomy inside safety envelopes that can be certified. In production settings, that hybrid approach is expected to outperform unconstrained learned policies. Physics-informed machine learning is part of that story. The point is not to make the model look smarter. The point is to embed physical constraints, so predictions and controls stay inside reality. When you are dealing with friction, wear, thermal limits, and material deformation, the physics is not optional. It is the ground truth you pay for. A second major finding is about digital twins. Many leaders treat a digital twin like a one-time simulation asset. In a programmable factory, the twin must stay synchronized with what the plant really is today. Tooling wear changes things. Sensors drift. Suppliers substitute parts. Operators make local adjustments. Maintenance introduces small differences that compound. If the twin does not track that evolving state, simulation to real validation becomes brittle. Then, factory as code quietly degrades into manual integration again. The twin becomes a pretty dashboard, rather than a trusted test environment for change control. So the interesting question is not, do we have a digital twin? The question is, do we have a living twin? Does it ingest telemetry? Does it track calibration? Does it capture process changes? Can it reproduce a fault? Can it predict what will happen after a software update? If not, your autonomy roadmap will keep snapping back to human firefighting. A third finding is that industrial IoT is less about sensors and more about governance. The sensor network control pattern is well understood. Connected factories are feasible. Yet interoperability, cybersecurity, latency, provenance, and operational accountability remain coordination constraints. Those constraints do not disappear with better hardware. They demand agreements, standards, and disciplined operating practice. Who is allowed to update a model? Who approves a new schedule policy? Where are the event logs? What is the rollback plan? What evidence exists for an auditor after an incident? This is where explainability stops being a marketing term and becomes a procurement requirement. Explainable AI is best understood as a family of methods and evaluation concerns. The question is not, can the model explain itself? The question is, what level of explanation is sufficient for the job at hand? An operator needs fast, actionable reasons. A maintenance engineer needs debugging traces. A safety team needs clear boundaries and failure modes. A regulator or internal auditor needs a record of what changed, when, and who approved it. Explanations must serve governance systems, not just developers. Here is the counterintuitive part. Higher autonomy can increase the burden of documentation. As machines take more decisions, the organization must raise its standard of audit artifacts, change control records, and incident review capability. Otherwise, the plant becomes fast, opaque, and fragile. A fourth finding is that exceptions are the real enemy of autonomy. Many failures are not local robot failures. They are coordination failures across enterprise systems. Late suppliers, non-conforming parts, energy curtailment, cyber incidents, maintenance shortages, demand swings that force last-minute retargeting. In those moments, the factory is not just controlling motors, it is negotiating priorities and authority. Which orders get delayed? Which quality rules can be relaxed, if any? Who is empowered to override an optimizer? Who signs off on a temporary process deviation? That is why reinforcement learning, optimization, and scheduling intelligence must be designed for override and audit. Optimization has to be robust in high-dimensional, constrained, disturbance-heavy environments. It must also be explainable enough to trust and stable enough to run every day. An optimizer that is brilliant but erratic will be disabled by the first plant manager who gets burned. So the most practical autonomy design is a layered one. Use explicit task graphs or behavior trees where maintainers can inspect the logic. Use decision tree-like policies where interpretation matters. Add learning where it helps, especially in perception and anomaly detection. Then put it all under a governance wrapper that controls when change is allowed. That brings us to the workforce shift, which is often misread. The autonomous factory is not mainly about removing people. It is about moving bottlenecks. Labor demand shifts toward diagnosis, certification, tooling design, data governance, and recovery authority. You will need robot cell programmers. You will need industrial data engineers. Simulation technicians become critical because validation becomes a daily activity. Safety case maintainers matter because the certified envelope is a living asset. AI incident reviewers will exist for factories the way they exist for security operations. Exception recovery leads become the new production heroes. If you do not plan for that shift, autonomy will stall. Systems will be installed, but not maintained. Models will drift. Calibration will decay. Workarounds will accumulate. The plant will run, but it will not become programmable. The procurement implications are concrete. Specify interoperability and audit artifacts before vendor selection. Require data schemas and event logs. Require model update records and interface documentation. Require safety case artifacts and clear exit rights. If you cannot substitute a controller, replace a vision system, or migrate a digital twin without requalifying everything, your future flexibility has already been sold. Risk policy also changes. Factory software updates must be treated as production events. They need versioned approval, rollback plans, simulated validation, physical trial limits, and post-deployment monitoring. A small software change can propagate across cells, lines, or even multiple plants. The failure mode is not one broken station. It is correlated outage. On longer horizons, the story expands. From 2026 to 2050, the frontier is reconfigurable cells and connected plants. Gains come from integration discipline, better perception, digital twins, safer control envelopes, and reduced commissioning time. From 2050 to 2100, bounded plant-scale autonomy becomes plausible in sectors with standardized materials, machine-readable workflows, mature safety cases, and interoperable plant software. Beyond that, factory as code could coordinate multi-plant networks with automated validation and institutional audit. Fully general factories that take arbitrary product descriptions and handle everything without human engineering remain speculative. So what changes for you? Right now. If you want autonomous factories later, Buy and govern reprogrammability today, because the future belongs to the plants that can change safely, quickly, and on purpose.